I'm going to go through the entire API, so new things like flow, like channels, but this is in essence a talk about Kotlin Coroutines, or how they work internally, what constructs it uses to allow for suspension of functions, to allow for building of coroutines and things like that. So before all that, let's talk a bit about me. I'm an Android developer at Five. It's a mobile agency in Croatia. We work on projects like the Rosetta Stone application for learning languages and the Crestone home automation system, something like that. So smart homes, really fun stuff. But it's not the only thing I am. So I usually do writing and speaking and mentoring. So anything where I can share my knowledge and share my experience if anyone wants to listen. And I'm also an Android tech editor and author at the Ray Vanderleek publication, which is really big in the US. And I'll talk about that a bit more later on. So about the talks. So I'll try to go through the brief history of asynchronous programming. Many of you use asynchronous programming, if not everyone. But it's really fun to look at the things we used to use 20 or 30 years ago, before I was born, to the things we use now in our modern Android and iOS applications, and to compare how things have changed or may have not changed. I'll also go about the coroutines and suspending functions in theory, so what they are and how they work internally, and about the inner works of the Kotlin Coroutines API. And at the end, I'll mention a bit about writing quality concurrency code, because even though coroutines are really fun to use, really cool to use, you can still write really crappy code which people will not understand or may break your system to some extent. So if you go back all the way to DOS, you had pretty much a single thread where you did one thing at a time. And if you did something that was really expensive, really computational heavy work, then you had to wait for that work to finish. You would be blocked until it fully executed before you could do something else, move to something else. And nowadays in Android applications we have many different ways of working with asynchronicity. So you could be downloading something in the background, uploading some files to the server, maybe synchronizing the application with some data like the backend and the database. You could also be doing some live updates for the application, all while showing a progress spinner to the user. And all that happens without the user knowing. So we really evolved from having to do one thing at a time to being able to do many things at the same time. But how do we do that? So usually in Android world, we rely on callbacks as a mechanism for communicating between threads, between results. But also we use Rx, which is really popular, and it has been hyped out in the past years. But if you look at all these mechanisms, or these two mechanisms, they all rely on really simple things like having threads, communicating between threads, and returning some results from a different thread. And when people think about coroutines, they always think of it as it's some kind of black magic, something that's really hard to understand, something that's really under the hood and you cannot wrap your head around it. But that's kind of the idea of my talk, so I'm going to try and demystify coroutines to you. I'm going to try to go through the API and explain things in a thorough way, just to prove that coroutines are nothing special. Well, to me they are, but nothing special in the system, at a system level or in programming in general. So when you want to learn about coroutines, you should probably learn how you can build them and how you can start them, which gives you the idea of coroutine builders, or the concept of coroutine builders. But then again, those coroutine builders build upon the concept of suspend functions, or suspendable functions in general, functions which don't have a linear execution flow. And all that builds upon the concepts of continuations and suspension points in code. When you grasp all that, you get to the coroutine scope, which is another mechanism coroutines use internally to make everything work. and the scope itself is powered by the coroutine context. So you look at all that, and you're probably thinking, how the hell am I going to learn all that? How am I going to understand all that? Well, I'm going to try to take the lot of it and explain to you in, let's say, a flow which made me understand it much better and much more easily. So we're going to start with the coroutine builders, of course. You can't use coroutines until you build them, right? Makes sense. So builders in general, one of the main builders is launch. It's just a simple function you call which creates a coroutine and lets you do something. For example, in this snippet of code, we would print something within a coroutine, right? But that's not just it. So this is a simple example. What happens in the background is what's important. So first of all, the launch function is an extension function of the coroutine scope interface, or the coroutine scope type. This means that you can only call coroutines from a coroutine scope. Kind of makes sense, right? Because of this limitation, you are kind of steered into the into quality code regarding coroutines. So you should never launch coroutines just because you can do that. You should always try to confine it to some scope, which I'll explain more later on, in order to have good life cycle of the coroutines and good, let's say, identity of the coroutine, so you know what the coroutine does, how it does it, and so on and so forth. So the other thing the coroutine builder launch takes in is the coroutine context, which is a set of elements which describes how the coroutine works. So for example, if you think of the context in Android, you have the context construct, which is pretty abstract, but it holds a lot of different things that define how your application works. If you take the context from one part of the application and build widgets or views with that context, you're going to apply the styles and resources from that context. It's similar in coroutines, so you have some coroutine context which you take in, and from there you build coroutines which are decorated by the context you give to the launch builder. After that, you can tell how the coroutine will be started. So it can be started in a couple of ways. One of the main ways is the default start, which is immediately. So when you launch a coroutine, it immediately begins with execution. You can also use lazy start in case you don't want to launch coroutines immediately, but rather want to wait for some condition or maybe launch them in parallel. And finally, the most important thing from the parameters is the coroutine scope suspension lambda with a receiver. So it's basically the bread and butter of coroutines. It's the block of code that's going to be executed in a coroutine, and it's the block that is going to be suspended if you need to suspend it. And it's also the block of code where you can suspend the coroutine yourself to wait for other coroutines and other threads and so on and so forth. But the job that is returned by the launch block is also a really important thing. It's a simple construct that pretty much is a piece of work encapsulated into a construct, which describes the state of the coroutine. So is it started, is it canceled? And you can also use it to provide your own cancellation and provide your own hierarchy of coroutines. So when we look at the job in general, instead of thinking it as something to make money off, it's a cancelable piece of work. It has a couple of lifecycle states, which we'll see in a bit. And you can also define parent-job-child relations, as I mentioned. So you can take one job and create a coroutine with that job. If that job gets canceled, all the coroutines get canceled as well. So you can define nice lifecycle, and basically the job is, in essence, the lifecycle of a coroutine. So when you start a coroutine, you first have the new state. And if you use the default start, the default coroutine start, it immediately goes into the starter state. If you have to use the lazy start, you have to call the start function yourself, and then it goes into this state. After that, it can complete, and it goes into the completing state, and also it can go into the finishing state where the coroutine is completely finished. So if everything goes well and you launch a coroutine, nothing bad happens, everything goes according to the plan, you should have this linear flow. But as I mentioned, the hierarchy of jobs, when the job is complete, it has to wait for all its children as well. So a job cannot complete without its children, so it has to wait for its kids. But if any of the kids or the job itself cancels or fails, everything goes into, let's say, a negative state or an unhappy path, and everything gets canceled. So once the first or any job in the hierarchy gets canceled, it will wait for the rest of the jobs, and all will go into the cancel state or the finish state. So jobs are pretty much simple in that way, that it can either finish in a good way or in a bad way. If one of the jobs finishes in a bad way, everything does. So using this, you can create complex flows which require a couple of API calls and a couple of coroutines in general. And then if everything relies on everything else, if something breaks, everything will break. And you can have a nice cancellation and a nice unhappy path, let's say, closure. So as I mentioned, the coroutine scope and all the job lifecycle happens within the scope. So a scope is just a way to bind the launch block or the coroutine to something that can be canceled and that can be monitored within your application. So if you look at this example, the launch block, the simple launch block with a print function, you can't really call it like that. One of the things you can do is call it within some coroutine scope, in this case the global scope. The global scope is pretty much what lives with your application. So if you use the global scope, you should really think about what you're doing with your code. Global scope should be used only for things that you fire and forget. For example, if you have some upload strategy, but you don't really require the result, you can use global scope to launch those upload functions and then upload the files without actually waiting for the result. If you don't really care about it happening in a certain thread or in a certain part of the application, it will run within the application itself, so within the lifecycle of the entire application. But one of the things you should do with your scope is create your own. For example, I have a snippet of code here from one of my projects where we have the base presenter, which is also the coroutine scope. So this presenter defines how the coroutines within will be executed in a way that if the presenter on destroy function is called, the scope itself will be canceled and all its coroutines as well. But before you actually provide that coroutine scope, which will be used for every single coroutine you launch within this presenter or any other presenter implementation, you have to provide the coroutine context. Here we provided the context using the dispatcher's default and the parent job, meaning that whenever we have a coroutine, it will be launched within the parent job, and if we cancel the entire scope of the coroutines will be canceled as well, as I mentioned before. I'll go back to this coroutine context in a bit. So now, when you're in the presenter, you can use the launch function as you would usually do it. And now you have default threading and default lifecycle handling behind this piece of code, and you don't really have to worry about that. So every single piece of asynchronous work which should be executed in the background thread can be done using a simple launch block. So regarding that coroutine context, as I mentioned, it's a set of elements which really define how coroutines work. And you're probably, well, at least I did, think of this image, and I thought of the Android context, which was pretty hard to grasp, as a beginner, and some people still have problems with that. But it's not actually that complex. It's not that hard to grasp the coroutine context, as it's really, as I mentioned, a set of elements which define how the coroutines behave. You have a couple of elements, and each of them dictate a certain part of the coroutine. So we have the lifecycle element, the threading element, and the exception handling element. As I mentioned, jobs are the lifecycle component. The threading component is the dispatchers class, which we used in the previous snippet of code. And the exception handling is another lifecycle or another coroutine context element which describes how exceptions are handled if something goes wrong in a coroutine. So when you look at this piece of code, we use the dispatcher's default threading component and the parent job lifecycle component. This means that every single coroutine which gets started within our presenter will use the background thread as its basis for running the operations, and the parent job for its life cycle. So if something goes wrong, everything gets cleaned up. If you look at the actual definition, it says that it's a persistent context for the coroutine, and it's just a bunch of elements which are described by their keys. Each key is just the implementation type, and you can find those contexts within these three classes or three interfaces. The jobs which implement the coroutine context interface. For lifecycle, the continuation interceptor, which kind of sounds a bit weird, but it's basically the threading, dispatching, or scheduling, if you want to call it like that. And there's also the coroutine exception handler construct, which is essentially just a small class which handles all your exceptions, which kind of makes sense. So about the interceptors and handlers, you can use those or think of those interceptors as a means to communicate between threads. So when you start a coroutine, it starts in a different thread. That's cool. But when you want to return a result, you have to do it through some construct within. You have to intercept the result and return it to a different thread. That's done through these dispatchers class or dispatcher class instances. So you have the main, IO, unconfined, and default instances. The main is used to publish to the main thread, so anything with a UI element can use the main dispatcher. The IO is used for big operations and IO operations, makes sense. So things like network calls, reading files, and so on and so forth. And the unconfined is a bit weird, but it's used for testing. The closest example you can take is the trampoline scheduler from RX, where it fixes all those threads together to make it work in untested environments. So in RX, you would usually use that to run tests, so you can have everything run on the same thread. That's what the unconfined dispatcher is. And of course, the default one is just a couple of schedulers, or rather threads in a worker pool, which help you work with anything in the background when you launch coroutines. They're just a real life for execution flows, nothing special. So when you look at this snippet of code, as I mentioned before, you can use the launch block, but you can also pass it in a context. In this example, we send the dispatcher's IO context, and we get some expensive result. The function can do whatever we want it to do, but the idea is that it will be done in a separate thread specified for heavy operations. After that, when you get the result, even if it's blocking, it doesn't really make sense because it's within a coroutine. After that, you get the result, you can launch back on the main thread and update the UI. So usually you'd have a lot of callbacks or a lot of RX wrangling here, which would set up the subscribe on and observe on schedulers, and then you would post the result through some callbacks. But you can simply use a launch block here to push it back to the main thread. Nothing really spectacular. Regarding the exception handler, well, it's pretty much what is used for handling exceptions. Kind of makes sense. You just get the context which you started the coroutine in, and if something crashes, you can use that context to restart a coroutine or maybe start something else. If you want to implement it, for example, let's say we have a launch block here where we use the custom exception handler as the context. For example, in this exception handler, we just check the type of the exception, and if it's an illegal argument exception, we just print out something. We can also print out the context we're in. Once you start the coroutine, we immediately throw within the launch block. What happens here is, even though an exception occurred and our program received an exception, the rest of the program will run perfectly fine. The while true loop will continue executing, and there will be nothing to give us, let's say, the feeling of that we failed our program, because the exception handler caught the exception and we can move on from there. We can just say, okay, this coroutine has died, but the rest of the program didn't. We can now use the context we used for the first coroutine, check the exception to see what happened, what went wrong, and we can start a different coroutine. It's pretty much that simple. But let's kind of go back a bit and talk about suspendable functions, let's say, core part of coroutines and what makes coroutines special compared to some other asynchronous mechanisms. Okay, they are pretty much regular functions with some low-level system support, let's say. They don't have to be executed in a linear way. For example, if you run a blocking request in Android using retrofit, it has to be fully executed before you can turn to the rest of the code, right? With suspension functions or suspendable functions, you don't really have to do that. So you can start a suspendable function, complete 30% of the work, let's say, and after that you can suspend it, wait for some more resources to be freed up, or wait until another function finishes, and then you can go back and continue working the rest of the 70% that you had. So they can be paused and resumed at any point in time. Just like threads can be suspended and resumed using the suspension counters in, on a system level, so can suspension functions, suspendable functions. But it's really cool to see this because you can call an asynchronous request within that function, and you can write sequential code which doesn't bring any more overhead to the process of learning how to work with asynchronous code. So yeah, as I mentioned, they have a suspend modifier in the end. We'll see how this works with the bytecode. So if you have this simple function which just prints out some data, and you decompile it to the bytecode, you get something like this. You get a static function which doesn't return anything, and it returns receives the data you passed in, checks it for non-null values because this is Kotlin and we don't really allow nulls, and it prints the data after the successful check. If you add this suspend modifier, this kind of changes a bit. It's still a static function, but now it returns a value, it returns an object, and not only does it take a data parameter, but it also takes something called a continuation. So what the system does in general is it says, okay, this is a suspend function, it has the modifier, I'm going to change the signature in a way that it can now return values, and it will receive another continuation parameter. The continuation parameter is going to be used as a low-level system callback, which will tell the function, okay, now is the time that you're suspended, and after a while, you should go all the way back and continue with your work. So it's just a low-level callback, or let's say a go-to statement, which jumps around your code and allows you to suspend and resume the function at any point in time. But what happens if you try to, add something a bit more, let's say, complicated? Here we added a delay call, which is another suspendable function call, and after that we just print some data. So nothing big should change, right? But that's not really the case. So just by adding one suspendable function, we get all this code, and let's kind of try to go through it a bit. The signature is the same, so we still receive the continuation and we return some object, right? But the beginning part is a lot changed. So what the system does here is says, okay, so now you have a function which has one suspension point in your code. This means that I will suspend once, and after that function is done, I will have to go back. So it creates a label and it creates a new continuation object, a new callback, which when called will return to that spot in code which the system first suspended. So here it does pretty much that. It creates the continuation, it stores the result within it, so it's a callback with some state, and it also changes its label to be, let's say, to reflect the amount of suspension points in your code. After that, it just returns the value of calling the same function, but this time without any data, because it's stored within the continuation, and by passing this continuation as the second parameter. So it kind of wraps around that function, delays for a bit, and then calls the same function after finishing itself, let's say. The rest of the code goes like this, and what it does here is it gets the value from or the result from the actual initial function call, from the continuation, and it also gets its label to see at which point in code we are now. The first time the function is ran, we get the label as 0, and it says, okay, so nothing happened up to this point. We haven't yet suspended, but we have one suspension point to go through. It increases the label by 1, and it calls the delay function to delay the entire suspendable function by 100 milliseconds, as in our previous code snippet. After it returns, it goes back to the same function, to the same case, and it says, okay, now the label is 1, I have some result, I have some data within, I can simply check if something went wrong. If nothing went wrong, I can go to the rest of the code, which is just printing the piece of data we sent in. So if you think about this, it's pretty much a small, low-level state machine where it has two states, the one where it didn't suspend yet and the one where it returned after the suspension. So the second state will be the rest of your code after suspension points, where the first state would be before you suspended anything. That's pretty much it, how it works within. But what happens if you add something a bit more complex than a delay, so an async call and an await call, which I'll cover a bit later on? Well, you get this. So this is 15 megabytes of decompiled code. This is a huge staircase of callbacks. And it's not actually anything to worry about because this is a bug in the decompiler itself. So when you try to decompile an async code, async block, the system or the Java system doesn't really know how to compile that, and it runs an infinite loop of code which you can't really run. So you don't have to see the whole staircase, just take the first step. But it's not the case here. You can't do anything with it. Why does this happen? Well, because of those suspension points, as I mentioned, the system knows, or the Kotlin system knows how to compile the suspension points, but the Java system doesn't. So let's see how it works in the Kotlin way. Whenever you add a suspension modifier, and whenever you call a suspendable function, you get this little sign next to your code, which says, okay, at these points in time, I'm going to suspend. And I'm going to create a state machine as before to check the labels and to see at which point in the execution we are now in. But it doesn't know how to do that with the await block, because what await essentially does is it says, okay, suspend this indefinitely until some result arrives. So it's basically like a future get, but it doesn't block any threads. It suspends indefinitely instead. So the compiler kind of breaks, and you don't really see any, reasonable code. But, when you look at this example again, and this huge piece of code, that's essentially what coroutines are. After you add a suspendable function and a suspension call or a suspension point, you get a small state machine which just, looks at the amount of suspension points in your functions and suspends that many times before it actually goes to the last label and counts all the suspension points and finishes the rest of the code. So this is done with the concept of continuations. As I mentioned, there are low-level callbacks, and the system actually has continuations within itself right now. So if you're using Java or any other language, the operating system uses continuations already, because it has to know how to go back to the previous function after your current function returns a value. So it's like a go-to statement, as I mentioned. And if you have the main function, the main process, you have the main process continuation, which if it returns a value or if it finishes, it will kill the entire process. Make sense? So when you call a regular function, you pass that main continuation to a different function. But you also hold the process continuation within the main function. And what happens here, if the getUser function returns a value, it says to the continuation, like a callback, take this value and pass it back to the place where you called getUser. So the compiler knows how to go on and use that result later on in your code. The same goes for the main continuation and the process continuation. So if something crashes, everything crashes, and all the exceptions, or rather the single exception, is propagated all the way down. But when you call a suspendable function, you have two continuations now. You have the getUser one in this case, when you call API call, and you have the suspendable one. Because the API call function is a suspendable function, and it can suspend any number of times within itself. So it has to use the suspend continuation to know where it is within the function itself, so within the API call function. After all that is done, it can simply take that result and pass it down to the get user continuation, which can be passed down to the main continuation and the process itself. And as I mentioned, regular functions have the continuations within themselves, but suspendable functions have two continuations which handle the function itself and the suspend part of the function. So as I mentioned, they can be cascade. You can propagate exceptions all the way down, or you can return values all the way down through any number of functions and any number of threads. They don't really create multiple stack entries, as you may think. They just reuse the same stack entry, but try to call the same code within itself because of the multiple execution flows in the code. So let's go on to the hands-on concepts. Let's say. As I mentioned, we usually use lambdas or some kind of callbacks and RX to communicate between threads. But using continuations and coroutines, we can do it in a different way. The usual ways of communicating between threads are using shared data, which is pretty volatile because you can have race conditions. You can use queues and polling mechanisms, which are really cool, but you can still write complex code, or you can still break something if you keep on polling for the value without anything coming from the other end. And you can also use futures and promises in different languages, but the problem of future is that they are blocking, so when you try to get the value, they will block the thread until the value is there. Coroutines won't do that. They will just suspend the thread until the actual value comes back. So that is done through the concept of the async await, and they provide an asynchronous mechanism to communicate between those threads without writing any special code, or without writing any or adding any overhead to the code itself or to the actual syntax of the code. They make it really sequential in this way that you can say, okay, launch a coroutine within the global scope and get me some expensive result using an async function. So what happens here is when you call async, you can pass it in the coroutine start parameter. By default, it starts immediately. So right under the expensive result value, the function can go on, but the result from the get expensive result is still being compiled or let's say executed. So it keeps on working on the result even though it's not there. And you can try to use that result by having to wait for it. So once you want to use the actual result, you don't get the result immediately. You get the deferred value. Once you call await, the compiler says, okay, so you are waiting for the result here, just like you would await for a future. But you're not going to block the coroutine or the thread. You're just going to suspend it. The thread which is handling the async block will keep on working until it returns the result. Once it returns the result, it will signalize the launch block that the result is there, and you can just print it out. This is pretty simple to understand, I guess, and pretty simple to write because it doesn't do anything hacky, so to say. The async block, just like the launch block, has a couple of parameters. You can also pass it in a different context, a different start if you want to have lazy async blocks. And you pass in a function which returns a value. It in return creates a coroutine which will hold the value within itself, so you can call that value whenever you want to use it. And what happens if you want to use multiple results? Well, you just call multiple async blocks. Because of the default coroutine start within the async block, when you call expensive result deferred and user deferred values, when you create them, they will both be executed in the same time, in parallel. And once you await for both of those results, you will suspend the entire coroutine and wait for two values, which, when compiled, are just going to be passed into a different function. So this is having parallel requests using coroutines. So nothing really hacky, nothing really complicated like RX zip operators or maybe merging the values or something like that. So what about safety? All this looks really good and maybe too good to be true. But what about safety in coroutines? So what happens here if we launch an expensive result function within an async block, we await for the result, suspending the entire coroutine. We try sleep for a bit so the actual request starts going, and then we try to cancel the coroutine. Usually, you'd think that the expensive result function will have to be executed completely before finishing, before canceling, but that's not the case. As I mentioned, since coroutines are suspendable by default, at any point in time of the execution of getExpensiveResult function, you can cancel, and the function will say, okay, so I may have done 30% of the network request or file reading, file writing, but you said I should cancel, and I'll just roll back that work and cancel it completely. So you don't really have to wait for the entire function to finish to cancel beforehand. So in that way, they're pretty safe. And even if you have the expensive result function as this, so a while true loop or an infinite loop, which doesn't really break any time because the sum condition is always going to be false. Even if the getExpensiveResult function is blocking and will always block, will never end, you can still cancel it, and the system, the process will know that it should be canceled and it should be stopped from execution. So it kind of does sound like black magic, to be honest. So with all that in mind, you should try to write structured and explicit code when writing coroutines. It's really easy to write coroutine code, but you should try to be really explicit about it. For example, you shouldn't use launch blocks when you're expecting a result from the network or something like that. You should use an async block. Additionally, you should be really explicit about your context, so you know when to switch which threads, which thread should be default for execution, and so on and so forth. You can also rely on the isActive flag of a parent. So if you're running while true loops in coroutines, that's perfectly fine because you can cancel them. But you should maybe try to rely on if the parent job or the context of that coroutine is active, because if anything else happens, anything bad happens within the coroutine itself, it will get canceled, but you can also cancel your work or maybe finish some piece of work before the entire coroutine gets cleaned up. So you can do some, final changes to your code or cancel the transaction and so forth. You should also try to use finite coroutine scopes. So try to avoid the global scope if you can, but rather go for scopes which are confined, for example, in Android to your activities, to your fragments, to your presenters or view models. And in essence, this is one of the things I really take to heart, is you don't have to know everything. So you can only start with the things that are useful to you, and then to switch to something else if you need to use that. For example, if you need to use flows for cold streams using coroutines, then you can switch to that, but you don't really have to learn about that beforehand. And to sum it up, coroutines use thread pools, which are pre-organized for you, so they don't really create any additional overhead. They use smart low-level callbacks to communicate between the threads and the functions themselves, so you don't have to do any thread communication or synchronization on your own. They do not block threads like regular code, but they suspend the thread until the work is done. So it's much easier to write code, and even if you, as I said, even if you write while true loops, you still won't block the thread or block the main threads and things like that. So you can really write amazing code and maybe not so good code and not break the system. And using a set of coroutine context elements, like your custom exception handler, your custom job relations, or your custom interceptors, you can write really cool coroutines and you can decorate them in any way you want. But in the end, coroutines are very easy to use and very clean. Also very safe when you think about all the things JetBrains has done regarding the cancellation. So you can really rely on coroutines to clean up your work even if something gets canceled, rather than having to wait for all that work to finish. And to intercept the question, should you use coroutines? In my opinion, if you rely on purely network calls and things that just return values, you should give it a go. But if you have a system which really relies on constant communication like Bluetooth or maybe some smart houses, something like that, then things like RX and streams are much better off than coroutines. So I would definitely recommend to you to play with them to see if they work for you. But you shouldn't just jump in and push coroutines in your code just for the fun of it. And here are some resources. There's a couple of projects on GitHub that I kind of try to keep up to date, but I get too busy at times, and I can't really update them. And there's also the Kotlin Coroutines by Tutorials book, which Nishan Srivastava and I wrote for the Raven publication. So you can also get that. We write about a lot of things in this book. It's out now, and we're just going for the second edition, which is going to introduce a lot of new things like the flows, as I mentioned, and things like that, new cancellation, and so on and so forth. And that's it. Thank you so much. Are there any questions or time for questions?